All right, so for this part of the notes, we are going to talk about the rules that we are following when an electron is basically filling up into an atom and the different ways we refer to those rules. And then we're going to talk about three different types of electron configurations. So we have an orbital diagram notation, we have kind of just your standard electron configuration notation that was like the manager's code in our boarding house activity. And then we also have noble gas notation, which is also it's just a shorthand way of writing electron configuration, okay? Because as we're moving down through, the higher energy levels or moving down our periodic table into greater and greater periods of the periodic table, these electron configurations start to get really, really long, okay? And so because of that, we want to have a way of writing them where we don't have to write so much. So let's go ahead and get to it. So here in the notes we're picking up, it says electron configurations, and it is the arrangement of electrons within an atom. It's like the electron address. Okay, so arrangement of electrons. Arrangement of electrons. All right, within an atom. Electrons in an atom tend to assume the arrangement that gives the atom the lowest energy possible because low energy systems are more stable than high energy systems. We've been really talking about this since, I don't know, it wasn't the first day of school, but pretty close. Um, our electrons like to be stable. And we also discussed in lab that, if we've excited an atom, um, unless the electron has ionized, meaning it's had so much energy that it actually lost an electron, um, then the electron wants to fall back down to this lower energy state. So it goes on to say the lowest possible energy arrangement of electrons in an atom, it's called the ground state electron configuration. So ground state. Okay. And there are three rules that govern the arrangement of electrons within an atom. We talked about these on our intro to electron configuration um, lesson. And you guys basically came up with these rules on your own. And now I'm going to tell you what they're called. Okay. So at first we have the Aufbau principle. All right. Basically, that word means to fill up. All right. So we're going to be entering electrons into orbitals of the lowest energy first. Lowest energy first. That means that we're going to have to start at the lowest energy level, okay, which is that 1s level. And then we're going to have to completely fill up all of the sublevels in the lower levels until we can move on to a higher level. All right, and so it's giving us an order for filling up our energy levels. And you may notice that it's like three, three, and then it says four, and then three. This is not a typo. Okay, so I'm going to explain in a little bit why this actually makes sense. Okay, the second rule, the Pauli exclusion principle. All right, think about when you're thinking about the Pauli exclusion principle, you want to really relate it back to like a single orbital. Okay, and he's basically saying that no more than two electrons can occupy the same orbital and they must spin in opposite directions. Okay. So we draw one up and one down. And then in this case, where we have three orbitals within a sublevel, we have to we have to draw up, up, up. Now this is actually a different rule. Okay, so Pauli is the one that, you would say, okay, two can fit in there, and one is spin up and one of them is spin down. But then it's our third rule, Hund's rule, that talks about how orbitals of equal energy must each have one electron with the same spin, okay, before an orbital is occupied by a second electron. So basically, we cannot pair up a downspin electron with an upspin electron in the same sublevel if all the orbitals within that sublevel do not contain an electron that is spinning in the same direction. Okay. So here's an example. If we have four electrons in that p orbital, All right, so this would be like our first box, second box, third box. We would have to fill one up, another up before we could fill one down. All right, so if you have not heard about this before, then definitely go watch the video where we do the boarding house analogy because you will definitely get it from there. Okay, so let's talk about the different ways that we can notate electron configuration. So the orbital diagram notation, here is an example of orbital diagram notation. You can also see orbital diagram notation with just lines at the bottom so it is lines at the bottom instead of just these boxes, okay? And you see how the box is just like completely, they're just laid out completely horizontally. And we're not really able to visualize like we are when they're stacked on top of each other, that say, for example, like the 2s sublevel is lower energy than the 2p sublevel. That's not something we can really visualize here, but you can see them in all these different ways, but they're called orbital diagrams, okay? And so because we know that the s sublevel only has one orbital, when we're drawing our orbital notation, we just draw one line. And then P has three orbitals. Okay. So we would just draw three together. Then D has five. So we would draw five. And then F has seven. So we would be drawing seven. Okay. All right, so that is how we would draw them. So we're going to practice that in a second. But one key thing to note, all right, is that the valence electrons, all right, so the valence electrons for an atom are located in your highest level S and P sublevels. Okay, so in this particular case, here are our highest level S and P sublevels, and we have one, two, three, four, five electrons being represented, and this is phosphorus. Okay, so let's just go see. Do I have phosphorus still on here somewhere? Yes, I do. All right, so here's phosphorus. Okay, according to the periodic table and what we've already learned, since phosphorus is in that five group 5A, all right, then we know that five valence electrons should be present, and that agrees with our orbital diagram. Okay, so valence electrons, they're in the highest level S and P sublevels. Okay. All right, we're going to try a little bit of practice. Okay, so it's saying draw the orbital diagram for the following elements. So at this point, if I were watching this video and I had my notes, I would just kind of take a pause here and do this and then see if you went in the same direction that I'm about to go in. Okay. All right, so we have silicone. Let's go find out how many electrons we need to represent. So 14 according to our periodic table. So we're going to have 14 electrons to account for. All right. Now, thinking about how our levels and sublevels are going to exist, we know that in that first energy level, all right, and you can look back at your notes as you're doing this because back in the part of your notes where it says sublevels and orbitals, you'll know how many lines to draw and how many electrons you're going to be able to account for. So in our first energy level, we have an S. Okay, so just one S and that is two electrons. All right, and so I've accounted for two. Now I'm moving to the second principal energy level. I have an S, okay, so that's my second energy level, and S is my sublevel, and I have a P, which has three orbitals. Okay, so this is 3p. And so let's just fill this up now. One, two, and so I got one, two. And then now I'm going to have six. We're going to go up, 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 down, down, down. That is six more. Okay, so I am at 10. And then now I'm going to jump up to my third. Oops, this should say two. Sorry. All right, that's the 2p level. All right, now I'm jumping up to my third principal energy level. And I'm always going to have the S. All right, so I'm going to start off with my S. I put my two electrons in there. I've got 12 now. And then I also next have a P. Okay, so 1, 2, 3. That's my 3p sublevel. And I'm going to only put 2 electrons there because that's all I need. Okay, so just 2 more, and now we have our electron configuration pretty much spelled out in orbital diagram form. Okay, it says how many valence electrons does silicon have and in which sublevels are they present? So we said that our valence electrons, they're in our highest S and P sublevels, and so we can count that we have 4 valence electrons. They are in 3s and 3p. If we go back to our periodic table and we look at silicon here, we can see that in fact we would expect that silicon would have 4 valence electrons. It's in group 4a. All right, so there we go. Then it says how many unpaired electrons does silicon have and where are they? So these two here are unpaired. So two um, unpaired, let's just say two unpaired, and they're in that 3p sublevel. Okay, so let's do iron now. All right. Iron is, of course, in that transition metal area. And so iron is farther down on the periodic table. And so we know that our electron configuration is going to be a bit longer because we have to account for all of these levels being filled up as we move from where we are starting from at that 1s level all the way up through whatever sublevel we're going to get to. So let's find iron on our periodic table. Okay, 26. Atomic number 26, that means that we're going to have 26 electrons. Why? Because, well, atomic number means that we have 26 protons, and protons and electrons are equal if we are a neutral atom, okay, like we are in this case. How do I know that? Well, mostly because I'm just telling you that that's the case. All right, we're just working with neutral atoms at this point in our lesson. So, okay, so we're going to account for 26 electrons. So we better get after it. Okay, so I'm kind of looking up above here. All right, so when I'm looking at silicone, I know I'm going to go through every one of the ones that silicone went through because silicone's atomic number is 14. Okay, so I've got to go well past that. But let's just start accounting for all these different ones. So we're going to have the 1s, the 2s, this is our 2p, our 3s, our 3p. All right, so let me just fill these in. 1s, 2s, 2p, 3s, 3p. All right, so we'll just fill these in. So 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so we have 18 so far. Now I'm going to start adding on. So we left off at 3p. Now we're going to go to that fourth energy level. All right, so the fourth energy level says we are at 4s. All right, so I said, how many did I say we have? 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, so we're at 20. We have 6 left. If we're at 20, we have 6 left. All right, so now we are in the Ds, okay? Because after our S level, according to our table, if we're in the fourth level, or I'm sorry, if we're in the third, well, we were in the third level. Um, but as we're moving down our periodic table, we're going to need to go back down, okay, to the third D. Okay, and I'm going to show you how that works in a minute. 1, 2, 3, 4, 5. Okay, we know we can have 5 in that sublevel. Okay, so we need to account for 6 more. Let's see, 10, 12. And so we're gonna go 1, 2, 3, 4, 5, 6. And so we should have an element ending in 3d6, which should be iron. So let's go look at a different view. Let's see if I can get to it. I want to show you guys what this looks like, here we are. Okay, so now that you're more familiar with these blocks, you have your S block, your P block, your D block, your F block. Okay, so I am going to just show you here how we're going to proceed through. Okay, so iron, if we had iron, let's see which one we're going to do here. Okay, so iron is right here. It's number 26. So it's 1, 2, 3, 4, 5, 6. So it's basically 6 elements into that third level of the D block. So that means that it's basically right here. Okay. Um, so we had to go all the way through these P's. So we went through these P's, and then we did 4s2. And then you'll notice that it dropped. Okay, now we're at 3 again. Well, how is that possible? Well, all of those transition metals that exist in that D block, whenever you are deciding which energy level to call them, just remember that you need to subtract 1 from your period number. So if we're in period 4 here, that means that these are going to be 3. And then if you when, not if, but when we get down to this F block, you're actually going to subtract 2. All right, so that is the case. But you don't jump right to them. So we don't go from 3s2 to 3d1. We have to go in the appropriate order. So we go S's, then the P's, then the S's again, and now 3Ds. All right. So I get that it's a little confusing at first, but we will do a lot of practice. Okay. All right, it says how many valence electrons does iron have and in which sublevels are they present? So our iron is going to have 1, 2, 3, 4, 5, 6, 7, 8. Nope. It's just going to have 2 here. It's just going to have 2 here. And it's in the 4s. So this is actually a really good here, 2 valence electrons, and it's in 4s. So this is a really good example. So remember how I was saying that we can have valence electrons and they're in the highest energy level S and P. Well, here we have the level 4s. Okay. So the 3s and the 3p, those are in a lower level. We don't have a 4p. Okay, but that's okay. We aren't going to use anything down here. Okay. So once we went to that fourth energy level, we're going to forget about the third energy level S and P, and we're just going to use the S in level 4, even though there's no P. All right. So I just want to make that clear. Then it says how many unpaired electrons do we have and where are they? We're going to have 4. We're going to have 4 unpaired electrons, one here, one here, one here, and one here. They are in the 3D sublevel. Okay, now we're going to talk about electron configuration notation. Electron configuration notation. That is basically our manager's code. Okay, so instead of writing it out in like an orbital diagram with boxes or lines where we're drawing arrows on them, now we're just going to draw the address straight out. Okay, so it says for a large number, it says the large number. Okay, so let me just write this big over here. Okay, we'll just write a couple of them. When it's saying the large number, it means these. Okay, so the large number is energy level. The small letter is the sublevel. The superscript is our number of electrons in the orbitals of the sublevel. All right, number of electrons in the orbital of the sublevel. All right, so now we're going to talk about these blocks of the periodic table. So I showed you one that was kind of colorful, and now I'm going to just kind of identify these blocks on the periodic table with you. Um, you don't need to color them, at least not on here, but in your practice packet is a very large periodic table, kind of like this one, and the assignment is to pretty much do what we just did, okay, or what you just saw, which was this really colorful periodic table, and you're going to label it and do all those things. So All right, so the S block is right here. Okay, it's like this. And you can imagine that helium is here. Okay, even though it's over here. All right. And then we have the D block. That is our transition metals, like so. And now our F block. Okay. And then down here, so this is, or I'm sorry, D block, P block, and this down here is the F block. These are those blocks we were referring to in the last video and in our notes when we're filling out that big table. Okay. All right. So when we're doing our electron configuration, we can use the periodic table to come up with this address, right? This electron configuration for every element on the periodic table. And so just for the sake of time, I'm not going to label every one of them. All right. But we're just going to get started here. Oops. Let's see if I can get rid of all of this. There we go. 3s, 4s, 5s, 6s, and 7s. These are all part of, like, all the ones within this box are part of the S block. All right. And then, just like we just did in that other practice problem, uh-oh, there we go. This is going to be 3D, 4D, 5D, and 6D, because in our D block, we must subtract, okay, subtract 1 from the period number. I know you guys remember what the periods are, right? All right, so if I were to just draw our periods, this is the first period, second period, third period, fourth period, fifth period, sixth period, six, seven period. Okay. Um, Now I'm moving over to the F or to our P block. All right, and so this would be our 2P, 3P, 4P, 5P, 6P. And then as we move down to this F block, when we're at the F block, remember, like, this is period 6 and this is period 7 because these inner transition metals are kind of like sandwiched in between. Um, and so because of that, we're actually going to subtract 2. So subtract 2 from the period number. Okay, so this then starts off at 4F because 6 minus 2 is 4, and then this would be 5F. All right. Okay, so now that we have this kind of set up, we can do some electron configurations. Okay. All right, so we're going to do fluorine first. So where is fluorine? Let's find fluorine. Fluorine is the very top halogen. Let me get a different color going. All right, so fluorine is our top halogen. It's right there. Okay. I could tell you already, without really having to do much, that my electron configuration is going to end in, let's see, 2p1, 2, 3, 4, 5. It has to end in 2p5, okay? Because this is 2p1, this is 2p2, this is 2p3, 2p4, etc. Okay, so that one will have to end in 2p5. But we're going to have to start at the lowest levels first. All right, so we have to fill up energy level 1 first, which we know just has one S sublevel. And then the second level, we know that we have an S sublevel and a P. Okay, S and a P. Um, and that should do it, right? Because we already know that we're going to end in 2p5 based on where fluorine is in the periodic table. All right, so let's go up 1, 2, 3, 4, and 5. No, that's not true. All right, it's 1, 2, 3, 4, 5, 6, 7. 8, 9. Okay, so fluorine should be atomic number 9, and it is. Okay, so this is just me demonstrating like how we would do it in orbital diagram. And now we're going to do it like this: 1s2, 2s2, 2p5. Okay, so that's how that would be. All right, now I'm going to do it without doing the orbital notation. We're going to go to calcium. Calcium, calcium. Let's find calcium on our periodic table. All right, calcium is 20. All right, it is the second, it's in the second spot in the S sublevel in that fourth energy level. Okay, so let me get a different color. Let's do orange, why not? So here's where calcium is. Okay, calcium has 20 protons, and so we're trying to account for 20 electrons here. Okay, here we go. 1s2. All right, that's 2. Then 2s2, that's 2 more. Then 2p6, okay, that's 1, 1, 2, 3, 4, 5, okay. And now, let's see here. We have to do 10 more. All right, so after 2p, we are going to go to, let's see here, 2p, we have to go to 3s, so 3s2, and then 3p6. Hey, Lizzie, I'm doing a video, honey, okay? It's all good. All right. So now we have 2p6. So we have, that's going to give us now 18. Thank you. Thank you. All right, that's 18. All right, 3p6. Now we're going to 4s2. Okay, so that's 2 more. Oops, let's put him like this, and we're there, right? So to double check and make sure that we have done this correctly, so I have done 1s2, 2s2, all the 2p6s, the 3s2, all the 3p6s, the 4s2, and now I've ended up where I'm supposed to end up. Now, if I have done this correctly, then all of these like superscripts will add up to 20, the electrons that we're accounting for. So we have 2, 4, 10, 12, 18, 20. Okay, so all these add up and we're good to go. All right, the next one that we're going to do is going to be really challenging. Okay, really challenging because we're going to have to go through the entire periodic table for the most part. All right, so we are going to do OG. Okay, what is it like? It's there he is. Okay, I'm not sure how to say that, but we're going to do it. 118 electrons to account for. So 118 electrons. I am going to zoom in super large so that we will have a lot of room here. Okay, we're going to have to go through pretty much all the blocks of the periodic table to get to this. So let's do that. Okay, so we're going to have 1s2 and then 2s2, 2p6, 3s2, 3p6, and then 4s2, then 3d10. Okay, because now we're in that transition metal area. Then we go back to the fourth level, 4p6, 5s2. Now we've got to subtract 1 because we're back down 4d10. And then after 4d10, we're back at 5p6, 6s2, 5d10, 6p6, 7s2, 6D, 10, 7P6. Okay, wait a minute. We have forgotten something. And by we, I mean me. Okay, after 7s2, we actually have to back up. Okay, it's actually after 6s2. So I was just moving through this thing too fast. Okay, after 6s2, let me just back this out. Oh, wow, that looks cool. All right, at 6s here, at this 6s, all right, after 6s2, which is this one, we have to go down here, okay, to include our transition metals. So we have to do that. So let's go back here. So after 6s2, now I'm going to say 4f14, okay? 4f14. And then now I'm back to my 5d10 and then my 6p6, 7s2. Now let's get my transition metals back in the mix. 5f14, 7p6. All right, that makes sense. All right, let's go look at this here. Okay, so um this the one that we're going for is right here. Okay. So I'm going to get a different color just to kind of like show you my progression through here. All right, we had here toward the end. Okay, we had 6s1, 6s2, then we jumped down here, okay, to the 4fs. We went all the way through the 4fs. But then after we were finished with the 4fs, we had to pick back up here at 5d and go through and then back to 6p. Okay, then we came back down here to 7s, and then we had to come back down here to the through this 5F block, and then back up here to the 6Ds, and then to the 7Ps. And that's how we got to 7P6. And so 7P6 has to be the last part of the electron configuration for that element, based on where it is on the periodic table. Okay, so it says, how do you check to see if it's right? We would basically be adding up all of these different things. Okay, we're adding up all these different superscripts. So now it wants to know, like it's giving us an electron configuration here, and it's basically just saying, is this what element is it? Okay, how do we check if it's right? So it's like I was saying before, if you know you're going to write the electron configuration for a certain element, the way you know that you have figured it out or you've done it correctly is that all these superscripts are going to equal your atomic number. And so it's 2, 4, and then this would be 10, 12, and then 17. Okay, so which element on our periodic table has atomic number 17? It is chlorine. So chlorine. All right. It says total of the superscripts equals the electron number, which equals the atomic number. Okay, equals the atomic number. Last part of electron configuration identifies the location of the element on the table. All right. So in this particular case, period, sublevel, fifth square. Okay, so looking back at this right here, this is what we're talking about. So if we're looking at chlorine, we know that chlorine, um, the last electron for chlorine will be in that third energy level and that p sublevel in the fifth square. Okay, it'll be the fifth one. And so that's where this thing comes into play. All right. So remember how we were doing this one earlier and we said, oh yeah, 7p6, that's the location of the last electron after the entire atom has been filled. Um, and so there it is. Pretty cool. Okay, What do we have to do next? Let's see here. All right, so let's do, um, I'm actually gonna, should I stop there? No, let's do it. All right, so here's a little bit of practice. All right, so I would pause this video and try this out and see if you can come up um, with this here. So here we have titanium, and so let's see how many electrons are we going to have for titanium? There it is, 22. All right, so we're gonna have 22. So we want to make sure that we're accounting for 22 electrons, and so we're just going to fill up starting at that lowest level first. So we know we have that 1s, 2s, 2p, okay? Then 3s, 3p. Where's that going to get us? That's 2. So that's the 1s level, the 2s level. I'm doing it in orbital notation, and then I'm going to do it in the electron configuration, just so you can kind of compare the two. All right, so this is 4, 5, 6, 7, 8, 9, 10. That's my 2p. And now I have 11, 12. That's my 3s. And then 13, 14, 15, 16, 17, 18. That's going to be my 3p. All right. And now I'm going to go to 4s. Oops. The s only has one orbital. 4s. Okay. 19, 20. And then now I'm going to have my 3d, which has 5. 1, 2, 3, 4, 5. And so I would have, I think, just 2. All right, let me count. 1, 2, 3, 4, 10, 12, 18, 20, 22. All right, so that's titanium. You know what? I actually just did the orbital diagram in the wrong place. All right, so I'm going to do the electron configuration now. One sec. I, hmm? My car keys? Can I give it to you in a minute? Okay, thanks. Okay, so here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d2. All right, we're going to just remember that this one on the top is the orbital diagram. I just wrote it in the wrong place. Orbital. And then on the bottom, it's the electron configuration. Okay. All right, we'll just finish up these last couple questions and then I'm gonna take a break. Okay, how many energy levels? The EL stands for energy levels. I don't know that I've ever seen it written like that. I bet we were just trying to save some space there. Energy level. All right, how many energy levels in an atom of titanium? Okay, so how many of them contain electrons? So we would say that we're going to have up to 4 energy levels with electrons. All right, we have 4 energy levels because we go all the way up to that 4, even though it's ending in 3. Okay, we do actually have 2 electrons in the fourth energy level. All right, how many orbitals contain electrons? All right, so we could count up, and if we counted up all of these, we would have 12 orbitals. That's like our singular lines. How many half-filled orbitals? We have 2 half-filled, and we have 10 full. And then how many electrons in the third energy level? We have 10. And how many electrons can go in an orbital? Just 2. All right, I'm going to go ahead and stop now. And then in part 2, I will go over noble gas shorthand. All right, thanks.